Study of thermal properties in commonly used fabrics using differential scanning calorimetry. Dsc, a forensic perspicacity. Abstract ignition or heating behavior of 6 different types of cloth material samples of different manufacturers in India was examined by quantitative thermal analysis method, i.e. differential scanning calorimetry, DSC, to find out if this parameter could be used in differentiating between these cloth samples and comparison of their tendency of self-heating possibility for forensic purpose. This study also focuses on giving a solution using the thermal analysis for analyzing the spontaneous fire accidents and for possible application in forensic study of fire cases. The results indicate that the transition heating temperature may serve as the useful criteria for differentiating different cloth samples from different sources. Moreover, thermogram of Dsc curve can be used as fingerprint to identify cloth material and presence of external material which may cause the self-ignition in fabric material. Thus, the cause of fire accident can be investigated. Keywords: thermal analysis, fire investigations, forensic science, thermodynamics. Introduction. Forensic science laboratories used to work with little amount of exhibit/samples collected by investigation personnel from crime scene to determine the type of material and its possible manufacturer for investigatory and evidence purpose. An example of it would be the characterization of polymers, plastics, cloth materials, etc. Such materials recovered from crime scenes of high destruction, such as fires or explosives, are often not in a state of conductive to a chemical analysis. Fibers and cloth materials are useful for forensic purposes, as they tend to cling easily and provide useful characteristics for identification purposes. The present paper focuses on the most useful and effective solution for analyzing and evaluating the cause of spontaneous fires, assessing the fire using thermoanalytical methods and the contemporary studies in this area for application in forensic fire accident examination. In most of the fire accident cases, self-heating can be one of the cause. Self-heating, also often called as spontaneous combustion or spontaneous ignition. Self-heating normally caused by exothermic chemical reactions or biological process. These are encountered especially in the fire accidents in industries and agricultural areas including forest fires. For the chemical reaction leading to a self-heating process, the theory of thermal explosion has been developed. One among the methods that have been used in forensic fire investigation is Mackey test 2. Which allows relatively rough statements and limited to certain classes of substances. To overcome and face such situation, the forensic scientists are presently using thermal or thermoanalytical methods 2 to 4. From a forensic point of view, thermal analysis, in particular differential scanning calorimetry, DSC, is useful for characterizing polymers, fibers, and highly self-ignition or fire-stimulating materials, traces, etc. 2 to 4. Because in it the required sample size is relatively small and very little sample preparation is required, which translate to fast analysis time. DSC is a technique that measures heat flow into or out of a material as a function of time or temperature. In a DSC measurement, information about thermal and mechanical history, processing influences, crystallinity, and curing, service temperature, is revealed by the first heating curve. For forensic comparison of chemically similar samples, thermal history plays an important role because subsequent controlled cooling creates a new known specimen history, which gives same characteristic properties to all materials. In the present paper, peak melting temperature, temperature of peak maximum, and area and delta H of the samples are recorded from the first heating curve to study fabric or cloth material. Material and methods. Methods generally used to study self-ignition are based on thermal analysis. Thermal analysis involves a large array of calorimetric methods, which usually require very small sample size and can also be used for unknown sample analysis. In the present study, heat flow differential scanning calorimetry, DSC, of make Perkin-Elmer and model No Pyrus 1 instrument was used for examination of cloth/fabric samples. Differential scanning calorimetry, DSC. Differential scanning calorimetry, or DSC, is a thermal analysis technique that looks at how a material's heat capacity, Cp, is changed by temperature. When a sample shows a transition, its heat capacity changes, and this is recorded as a change in the heat flow. This heat flow allows the detection of phase transitions such as melting, glass transitions, phase changes, and cross-linking. Sample compositional analysis and effect of additives can also be examined by this method. Semicrystalline material and their critical thermophysical properties like melting temperature, heat of melting, percent of crystallinity, glass transition temperature and processing temperature can be studied using DSC. In experimentation using DSC, the sample is put in crimped aluminum pan and the reference, usually an empty pan, sits on raised platform on the sensors. As heat is transferred through the sensor, the differential heat flow to the sample and reference is monitored by present area thermocouples. A thermocouple monitors sample temperature. A preheated purge gas, i.e. nitrogen, is present to provide additional baseline stability as well as the desired sample/atmosphere interaction. Polymers are potent source of fuel for fire and have inherent inflammability. Most fabrics ignite and continue to burn even after the source of ignition is removed. To utilize and improving the flame-resistant clothing, Dsc is used for characterization of different fibers of the fabrics and textile. A typical Dsc curve while heating synthetic fibers is shown in Figure 1. Figure 1, illustration of different thermal events in a typical Dsc curve. To understand the behavior of Dsc curve and for its proper evaluation, it is important to know the various thermal properties and their correlation. These important formulas are as follows. Equals. H the change of enthalpy between two states, Cp specific heat capacity, the quantity of energy needed to change the temperature of 1 g of material by 1 degree Celsius at constant pressure and T temperature. Here, Cp is hard to measure, thus heat flux calculations is used in place of Cp as it is correlated as follows. Equals. Q heat flux the quantity of heat transferred per unit time and mass. A heating rate and m total mass of substance. Equals. Here F represents the total area under transition peak. In the present study, 6 samples of commonly used fabric or cloth material, manufactured and supplied in India, have been used. I.e. nylon, wool, rayon, polyester, terry cotton, and cotton. These samples of cloths are analyzed over the temperature range from 25 OC up to max 350 OC. A heating rate of 15 OC/min and 20 OC/min was used with nitrogen atmosphere around the sample. Results and discussions. Displayed in Figure 2a, are the Dsc results obtained on the first cloth material sample, i.e. for nylon. The plot shows the heat flow as a function of sample temperature and an endothermic response is oriented upwards. The cloth sample provides a substantial amount of characterization information with the Dsc. A melting peak is obtained at 220.93 degrees Celsius with a heat of melting of 97.92 J/G. Additional endothermic peaks are observed at 194 and 215 degrees Celsius, and these are most likely due to processing or heat setting. Similarly, for Figure 2b, Dsc curve results show that the sample, i.e. wool cloth material, has a melting peak at 130.13 degrees Celsius, with a heat of melting of 197.98 J/G. A. B. Figure 2. Shows Dsc curve obtained from experimental studies done using different type of cloth samples, i.e. for A. Nylon, B. Wool. In Figure 3, A. Dsc curve results show that the rayon cloth material has a melting peak at 250.66 degrees Celsius, with a heat of melting of 78.68 J/G, whereas, in Fig 3, B, the pseudo-endothermic event observed at 96.44 OC in thermogram is due to a volume relaxation phenomenon occurring at the glass transition temperature, Tg, of the polyethylene terephthalate, PET. This is the result of a physical aging process which gives rise to an ordering of the amorphous molecules when the material is stored for extended periods at temperatures below Tg. The melting temperature of polyester is 252.29 degrees Celsius and the enthalpy required to melt this polyester fiber was 23.10 J/G. Dsc results obtained when terry cotton and cotton cloth fabric sample was loaded is displayed in Figure 4a and 4b. From these thermogram we can differentiate the properties of these fabric and observed a melting peak of terry cotton at 109.44 degrees Celsius temperature with a heat of 98.31 J/G, whereas for cotton sample its temperature of melting is 111.16 degrees Celsius with the heat of 120.23 J/G. A. B. Figure 3. Shows Dsc curve obtained from experimental studies done using 2 different type of cloth samples, i.e. for A. Rayon, B. Polyester. B. Figure 4. Shows Dsc curve obtained from experimental studies done using 2 different type of cloth samples, i.e. for A. Terry cotton, B. Cotton. Table. Point 1 Analysis of Dsc curve and details. S.No cloth material name Dsc curve properties. From Figure 2, 3 and 4 it is clear that different fabric material got burned by absorbing a particular amount of heat at particular temperature. From these Dsc results for pure cloth material fiber it is clear that self-heating in these cloth material is rare at measured temperature ranges, as no any exothermic peaks are visible at given temperature range. For detailed analysis and comparative study of their thermal behavior, results for these cloth material is tabulated in Table 1 and plotted in Figure 5. See Figure 5. Comparison of all cloth sample on the basis of their a. melting point, b. corresponding heat enthalpy and c. area under peak to compare their tendency of ignition and heat energy required. Identification of fabric materials and comment on their tendency of spontaneous ignition. As per comparative chart shown in Figure 5, we can conclude that polyester needed minimum heat energy and heat flux for transition, due to which it generally tends to melt fast when external ignition is provided, but its transition melting temperature is maximum among samples, which makes it very bad as a self-heating cloth material. Whereas cotton and wool tends to burn at low temperature, thus may catch fire, or tends to self-heating when surrounding temperature is slightly higher than 100 OC, but the heat enthalpy and heat flux required to initiate transition is high as compared to other samples. Thus from the present study we can conclude that the particular thermal characteristics from these cloth sample specimen can be used for recognizing the particular cloth material condition found at the fire accident cases. The observed thermal properties of these cloth samples are valuable for forensic purposes, since they can provide a fingerprint of the material which can aid in tracking down the particular manufacturer of any fabric yarn, like for shirt, curtain, carpet, and bed sheet, etc. It can be seen in Table 1 and Figure 5, c, that for fabric of a different materials the values of peak melting temperature are different. As compared to other cloth materials discussed here, high cellulose content makes cotton particularly most liable to catch fire through external ignition. Therefore, while investigating fire accident cases, we should check around the possibility of presence of sparks, fire, naked lights, and lit cigarettes traces, etc. In addition to external ignition, cotton and other cloth materials are also liable to thermal, chemical and microbial self-heating/spontaneous combustion. Self-heating/spontaneous combustion arises as a result of moisture, fat/oils, due to the action of acids, such as nitric or sulfuric acid, and through contact with oxidizing agents and with goods with a tendency to self-heating. Thus, if from cloth samples received from fire accident crime scene these type of traces of self-heating material is present, then it can be checked by Dsc curve results comparison, as it may help in assessing to investigate the possibility of an ignition. Conclusion. This study clearly shows that most of the cloth material, i.e. fabric used for daily wear cloth, home decor, and for furniture have very rare tendency of self-heating as per experimental results shown in this paper. But in the presence of external ignition stimulation material, these material may tends to caught by fire. Whenever there is a case of fire accident or burned body, etc., the collection of cloth pieces found at that place and from burned or buried body can leads to important clue regarding investigation cause of accident or murder. As examination of such cloth material using Dsc can be used as fingerprint for cloth material, and presence of external material can be identified due to which self-ignition or deliberately ignition was caused. In the present study we have used pure cloth material samples of 6 different fabric to investigate their self-heating tendency. As a future extension of this work, lab prepared samples of cloth material soaked in flammable material in burned, half-burned, and unburned state can be tested. This study will help to clearly differentiate between fingerprint region of cloth material and its thermal behavior in presence of external material and their traces. Acknowledgement. The authors are gratefully acknowledge the support and encouragement provided by Director cum CFS, DFSS, Delhi, and Director, CFSL Hyderabad.